Also, thank you for the kind invitation. It's my great honor to be here for the first time. And I'm Zhou from Chinese Academy of Science. And today I'm going to talk about something on numerical PDEs based on neural network functions, which this is a very hot topic in recent years. I was majoring in uncertain quantification and numerical PDE a few years ago, but recently I have to catch this topic because this is too hot in China. So otherwise you will not get money actually from the government. So today I will talk about something on this topic based on the research work in a couple of years. The talk will be divided into 4 parts. I will give you a very brief introduction for deep neural networks. I think most of you should be very familiar with this type of functions. Then I will talk about mainly on this topic, the so-called failure-informed adaptive sampling for pins. Essentially, this is the idea of how to choose the training points for pins when you use this method to solve a PDE. So one of the key issues how to choose the training points. Similarly, you can do the same thing, so-called deep breeze method. Deep breeze is just based on the variational formula of the PDE, a different type of method using deep neural networks. And then in the final, I will give you some conclusions. And this is a very brief introduction for the deep neural networks. Actually, the deep neural networks were just define the functional space. This one neural network function is just a nonlinear function with a few parameters here. First, the dimension of the parameters should be very high, so that they have a very high capacity to approximate a complex function. And actually, the later neural network structure were defined like this. You just based on in each layer, you will have a very simple transformation. This is the linear transformation, and then you will have an activation function here, which is nonlinear. Otherwise, the whole transformation will be linear, which is not useful for approximation. So this is important. You use an activation function here, so that the entire is and it can be very complicated. So normally we will define this kind of things, I here and BI, the unknown parameters. We just denote these unknown parameters by theta here. So the idea is to decide the state based on the purpose when you use this neural network function. This is the traditional choices for the activation functions of large number of choices. And another issue is how to define the neural network structure.
저기
fully
진짜 편한 거.
connected neural network and different structure for the neural network architecture, which you can design your own architecture. And you can see that based on these tools, actually, they are very successful in industrial applications, which is due to mainly by the demand of OpenAI. And mathematically, there are a lot of things to do. Actually, the first one is how to define the functional space based on neural network functions. But classical methods such as finite element and spectral method, we usually work with polynomials locally or globally, the polynomial space, and then Sobolev space. So now the framework is to use neural network functions. So the basic problem is how to define this functional space and what type of function are you considering. But this is the basic problem. You can see there are a lot of works on this topic recently by Wei Nan Yi and Jin Chaoxu, a lot of other guys. And also, sometimes you are facing a problem of approximating a probability function. But this is actually the essential idea for the ChatGPT. Behind the story, actually, you are approximating a very complicated probability distribution. So most of the large language model is doing things like this. And also, AlphaGo is kind of a Barman equation. You are doing the reinforcement learning. So a big success in industry applications, but for scientific computing, it's not that successful actually. Today I'm going to talk about the very simple problems to solve a very simple PDE. You know that we have a lot of traditional methods to do this. If consider this is a very simple PDE, and this is the PDE equation, and this is the boundary condition. And in this operator, there are derivatives and other terms. And you can imagine that this is simply the Poisson equation or elliptic equation. For this kind of PDEs, you have many classical methods such as finite element, where you use some local polynomials to approximate solution, the linear finite element or second order quadratic finite element. And also you can consider the spectrum method where you use the global polynomial approximation in the whole domain. So this is a popular method to solve this PDE. But now it seems that many people want to use neural networks to solve this kind of PDE. I think the main reason is that it might be possible to handle high-dimensional problems. Can be possible. Actually, if you use finite element or spectrum method, you can't imagine to solve a very high-dimensional PDE because all of the methods are based on meshes or based on the tensor product approximation. So which is not a good framework for the high-dimensional problem. So the one reason is that neural network function may be a good thing to use for high-dimensional problems. The other one is actually based on PyTorch and the TensorFlow. The coding part is very easy, actually, very friendly to our students and master students. So normally, when you solve a PDE, only a few codes you need to do. So it's very easy to get started. So this is the two main reasons for using neural network functions to solve this PDE. But for this kind of PDE, actually, you can see that there are many different names for the neural network approximations. The first one I list here is the so-called deep breeze method, which is given by Vinay in 2018. The idea is to use the variation formula of the PDE. We begin with the variation formula of the PDE. So the starting point is that for the PDE you consider that there should be a variation formula there. Otherwise, you can't use the so-called deep breeze method. The Pins method is just to deal with directly the PDE itself. Suppose you consider second order PDE, you will do the pins with the original PDE, but in deep breeze you will change the PDE into the variation formula, which means that for second order PDE you will consider only first order system. You only need to face the first order derivative in the variation formula. Also, there are another framework called WAN. This is one by Gumball and other co-authors. This is based on the so-called wake formula. When you use finite element to solve a PDE, you begin with some wake formula. And this is the same. You begin with some kind of wake formula and you model the solution with neural network, and you also model the test function with neural network. That's the name. That's where the name comes from. It's wake adversarial neural network. You consider the balance between the test function and the solution itself. That's where the name comes. So today I'm going to talk about the adaptivity for these two methods, but idea can be extended to other framework actually. So the first part is failure informed adaptive sampling for pins. To begin, I will give you some very brief introduction to the pins method. Consider this PDE and with boundary condition. In pins method, you want to approximate the solution U here by a neural network function. I just modeled the solution with a neural network function. So the idea is to decide this unknown parameters here in the neural network. And then you approximate the solution with this neural network function. The function should satisfy this equation and the boundary condition. So you put this function into the equation, you will get the residual of the equation here, which is denoted by R here. And the other one is the boundary condition. The solution also satisfies the boundary condition. So you will get another term for the boundary condition. So this is the so-called loss function for pins. The idea is to minimize this loss function, because if this is the good approximation for the solution, this should be 0, and the other one should also be 0. So the idea is just to minimize this loss function to obtain the optimal state here. So in this way, you will get an approximation U here. But this is very easy actually. If you solve this PDE with the neural network function, actually you can just a few lines will get the solution. So the coding procedure is very easy. So the next, you have to deal with this optimization problem. And to solve this problem, actually, you have to describe this kind of a norm here, because this residue is defined like this. And this, you put the neural network function here, and you obtain this L2. Usually, you will consider the L2 norm residue and also the boundary term. When you solve this problem, you have to describe this continuous norm. That's why you want to choose the training points. So to compute this optimization problems, usually you were sampling the domain and boundary. You were sampling the domain to obtain the training points for the domain, for the solution, for the equation. And then you were also sampling the boundary to get the boundary loss here. So in this way, you will get the discrete loss here, which is only depend on the unknown parameter set here. So remember that the set is a very high dimensional parameter space. So then you will optimize this discrete the loss function here. So actually, in this step, you can see that there is a statistical error when you're sampling the domain. So this is similar as the infinite element method. When you do finite element, you first need to get a match, and then based on that match, you will discrete the solution. You define your finite elements spaces. But here it's the same. But we no longer use finite element. We use neural network functions, still some nonlinear functions to approximate the solution. But you have to sampling the domain and boundary to get the training points. But how to sampling is similar as in finite element, how to refine a mesh. So in this step, you will introduce some error. We call this statistical error because actually when you're facing high dimensional and complex problems, normally you will randomly choose the points. The points should not be structured. Otherwise, you will not solve high dimensional problems. And like in finite element method, you are based on the structure mesh. The mesh can deal with one dimension until three-dimensional case. But for high dimensional case, that's not the framework. Usually, you're just randomly sampling the whole domain. So here, the key point is how to sample. This is the main topic of this talk. But you can also argue that how to choose the activation function, how to choose the base in the neural network functions. So that's another topics. But there are a lot of topics to do actually. But here we just focus on one of them. It's how to sampling the domain, how to choose the training points. So as I just mentioned, you can make a comparison between finite element method and the deep learning method. In finite element method, in the beginning we have a mesh. We have a mesh, and based on the mesh, we will define the local polynomial basis, and based on this basis, we will approximate the solution. But here in deep neural network approximations, we will use some neural network functions as the approximation framework. And then we need samples to train this neural network function. So the samples should be a good sample size in the domain. A good means that it should be coincide with the solution, not necessarily uniform distributed. Remember that in finite element method, I think that the biggest success is to develop the so-called adaptive finite element method, meaning that for singular solutions, for PDE with singular solutions or very complex solutions, you have to refine the mesh to develop adaptive finite element methods. Otherwise, you will not resolve the PDE solution. Suppose a PDE have a singularity in the middle of the domain. If you use uniformly distributed mesh, you will not resolve the solution. So you have to do the same thing here, exactly the same thing here. So the big issue in finite element methods is how to define the mesh, how to refine the mesh. That's the main issue for adaptive finite element. You have a lot of techniques to do this posterior error indicator and R refinement and P refinement and also moving mesh method. All these methods are developed in adaptive finite element method. But here you have to do the same thing for neural network functions for pins. So how to choose the training points. You have to refine the training points. In the beginning, normally you will begin with uniformly distributed samples. But based on these samples, you can't recover the singular solutions actually in general. So you have to refine your training points, similar as you have done in finite element method. So the idea is actually very simple. Consider this problem is very clear actually. The problem is just to minimize this residual here. Actually, this residual is defined like this. And then the next step is sampling this domain to choose the training point to discrete this continuous law. But how to choose the samples? This is it can be very flexible. You can use arbitrary density to generate samples. This is equal to this quantity actually. You can choose any density function here. They are equivalent. So actually, the most efficient density here should be like this. This is the basic idea for importance sampling. If you want to approximate this integral here, the best sampling scheme should be like this. The P should be chosen like this. But the problem is that this residual is unknown. So the optimal way exists, but actually currently you don't know the exact residual here. So the optimal is there, but in the current step you can't use it. So actually the problem is very clear actually. So instead of using the optimal way to sampling the domain, actually you can do some kind of approximate importance sampling. The idea is just to choose a density such that the residue is uniformly distributed. This is very similar as in finite element. Why you want to refine the mesh? You want to refine the mesh so that in each single mesh, the error is uniformly distributed. That's the purpose you develop a posterior error indicator. If the indicator is large, then you will refine the local mesh so that in each mesh the error will be small. So this is a uniformly distributed principle. This is very similar in finite element method. So the idea here is also the similar. So in the beginning, you don't have anything about you don't have any information about the residue. The only thing you should do is to refine the whole domain by uniform mesh. And then once you after the computation, you will get information of the residue, and based on that, or based on the error indicator in finite element, you can refine the mesh and repeat the computation. And this is the adaptive finite element. And here we call this deep adaptive sampling, given 4 pins. So the idea is very simple. So like in finite element methods, you will define some kind of error indicator. Because here you are minimizing the residue. So we just define that if the residue is larger than a tolerance, then it means that in this point, the residue is not good. But this is unlike in finite element method. You can do this in a single mesh, mesh by mesh, because the mesh are structured. You can consider a single mesh, and if the error is large, and then you divide this mesh into 2 mesh. But actually here we don't have a structured mesh. We just have random samplings, random points. So this is the idea of a statistical. It's not a structured method. So we are care about how many points are larger than a tolerance. It's not a single point because the points are not structured. We just care about how many points out of the whole training points are larger than the tolerance. We call this the failure probability. It defines that if you have 1,000 training points and you have 10 points that are larger than the tolerance, then the failure probability is like 1%, something like that. You care about a probability, not a single point. This is the main difference between finite element method and here. In finite element method, you can consider a single structure because the structure is, the whole mesh is structured. So the idea is to adaptively to find this failure probability. And this can be viewed as the error indicator in finite element method. In finite element method, you have to derive some error indicator. And after each iteration, you will compute an indicator and to refine the mesh, and then repeat the computation, and then refine the mesh. Here is the same. Here, the indicator is the failure probability. You will define another tolerance for the failure probability, epsilon p here, because for example, you can define that the epsilon p is 1%. If the failure probability is larger than this one, then you will add new training points to the training sets. But how to add the points based on the residual information. So this is the whole adaptivity procedure. And to do this, actually, you can have a very naive approximation. As I mentioned in the beginning, you always use uniform distributed points as the training points to begin your training for the neural network. After a few steps for training, then you will get some information from the residue. And in the current step, you can, based on this residue, to refine the points. But how to refine the points? You can still generate a lot of points uniformly in a domain, and for each domain, you can compute the residue, because in the current step, you have some information for the residue. You have trained the neural network, you get the residue, get an approximate residue. And based on that residue, you can which point is large, and then you add the largest point into the former training set. This is straightforward. I mean, in each step, you will generate a large number of points based on uniform sampling. And for each point, you will compute the current residue. And you choose the largest points into the former training sets. This is called RAR. The main difference is that in each iteration, you are generating candidate points by uniform sampling. And you will compute the residual information for all the points and choose the largest 100 or largest 10 into the former training size. This is the so-called RAR, which is by Kanidakis. But this is a straightforward adaptivity for pins. But you can imagine that this can be very inefficient. Because as I said, that the singularity is local distributed. You can't use uniform sampling in each step to find the new points, to add this new point to the training set. So you have to do this in the important sampling way, as I mentioned before. So the best way to do this is actually in each step, you should sampling with optimum density. In each step, you have a residue. This residue is approximated one. It's not exactly residue, but based on this, you have optimum density related to this current residue, right? This is similar as the very beginning. Suppose this is known, then you have an optimal way to sampling the domain. But in each step, actually, you have approximate residue. The residue are related to the optimal density there. So you have to change the density step by step. After each iteration, I mean, here iteration is the adaptivity iteration, not the training for the neural network SD, not that iteration. So in each iteration, you have an optimal way to sampling. But as I mentioned, that if you want to use this optimal density, you have to use the full information of the current residue, which can be also very complicated. So you can do a very similar way to do this actually. This is optimal in the current stage, but it's optimal, but it's based on the whole information of the residue. You don't need to do this. The thing, but how to do this? Actually, you can do something between. The optimal way is optimal, but it's very hard to compute. And RAR, you don't do anything. Anytime you will begin with uniform sampling. And based on the current residue, you choose some points of the uniform points. You didn't do anything here. Here you want to do the optimal way, which is time consuming. So the idea is to do something between. In each iteration, you can simply use a very simple random variable to model the optimum density. Optimum density is very complicated. You have to use the whole information of the residue. But you don't need to do that. You just need to use a very simple random variable. Suppose in each iteration, I just want to use the truncated Gaussian. Truncated means you have to concentrate the points in the finite domain. If you consider the whole domain, you don't need to truncate. Suppose that each iteration, I just consider Gaussian random variable. I will not consider the so-called optimum density. I just in each iteration, I just want to use a Gaussian random variable to model the so-called optimum density. So I only need to compute the mean and the variance of the random variable. And this were based on the failure points in the last step. In the last step, you have collected some failure points, which means that for these points, the residue is very large, larger than your tolerance. And in the last step, you have a few points information, and based on that information, you will estimate the mean and the variance for the next time, for the next step. In the next step, you will use this kind of a Gaussian random variable as a Gaussian distribution to model this so-called optimum density. And based on this, you can compute the failure probability in the next step and to generate a new point also based on this density. Because you are always doing something in the failure region. These points are failure points. So next time, if you generate by this density with high probability, the points are all failure. It means that for that points, the residual should be very large. So you add these points into the training set should work. That's the basic idea. And doing this do not need any computational resources compared to training a neural network. You just do some very simple computation. It can be negligible compared to the training of the neural network, right? So the idea is to use Gaussian random variable. You can use other type of density. Gaussian, not beyond Gaussian density, but here, this is the most simple way to do this. So this is actually the so-called posterior stasis error analysis. This is similar as in finite element. Finite elements, we call this posterior error indicator, posterior error analysis in finite elements. But here, we just want to estimate the failure probability in each step. If the probability is less than the tolerance, then we'll end the computation. Otherwise, we'll add new points to the training points and restart the training procedure. So how to add the points? It just generate a new point with this Gaussian random variable. Then by this, you are doing adaptivity in the training procedure. And for this algorithm, actually, you can derive some upper bound, error bound for the whole algorithm. But this is the whole procedure. It's very simple. It's just a few you update. You only need to update 1 or 2 lines in the pins methods. A few lines will finish all the procedure. You're just sampling uniformly in the beginning, and then based on the residue, you will compute the so-called Gaussian density, and then compute the failure probability. If it's still large, you generate some new points to add them to the former training size and repeat computation. So this is very easy, and you can derive an upper bound from the algorithm. It says that the approximation solution for the exact solution is bounded by these 2 tolerance, where this is the residual tolerance is a 1-order scheme, and for this probability error tolerance, this is a half order. So actually, the dominant term is probability tolerance, which is reasonable because this is a statistical method. You care about the probability, not a single point. So let me show you a very simple example. You can understand how it works. This is the most simple Berg's equation, and the solution admits a very discontinuous structure. If you solve these problems with the traditional pins methods, it goes like this. It will not converge for sure, because the solution is not smooth. If you directly use the pins method, you will need a very large, huge number of training points to obtain the accuracy. Otherwise, the method will not converge. And you can use the RAR, as I mentioned, which is not efficient. They will improve the accuracy. But if you use the algorithm I just mentioned, the only thing you need is in each step you will compute the Gaussian density. You don't need to do much things. And this is the exact solution. I just computed the solution in the space-time domain. The methods works like this, actually. You can see that there are small points in the background for the computational domain. For this example, I just view the equivalence of x and t. I just view the time variable and the physical variables as the same thing. So I just computed this two-dimensional problems. And in the beginning, you don't have any information for the residual. So you have to choose the training points for the whole domain uniformly. This is standard pin, what to pin do actually. This is the initial training points. And after the one iteration, I will generate some red points here. This is is continuous line for the solution actually. It's a x, it's a t. This is the continuous line. After the second iteration, I will add some black points here. The third iteration, the green points here. So you can see each iteration, you will add some very efficient points into the training points, into the singular region. And this is for comparison, this is the RAR method by George. You can see that background points is very small. It's still, you begin with uniform points. But in each iteration, have also choose some point from uniform distribution. So after first iteration, you will add some red points here. And the second iteration, you add a few black points here. And the third iteration, the green points. You can see that this also works, but not that efficient. But if you do a little bit thing, just compute a Gaussian random variable, then you will the algorithm becomes very efficient. So this is the idea. You don't do much things actually. This is the efficiency. Well, this is the numerical bounds. Error bound indeed that this is the half order and this is one order. And this is another example. This is a high dimensional problem. If you consider a very high dimensional problem, actually the adaptivity is more important, much more important. Because actually the resource is you use it only allows you to use a finite number of training points, a finite number of iterations. Actually, based on these resources, in the high dimensional case, actually, you can the points in the high dimensional space is very sparse. So for high dimensional problems, the adaptivity is much more important. Otherwise, the method will not converge for the high dimensional problem. So currently, I just introduced a very basic idea, similar to the infinite element method, and very simple. And in each iteration, you have a rough residual information, and based on this, you will estimate a Gaussian density function, meaning that you only need to compute a mean function and a variance function. And based on this, you will do the adaptivity, and this can be very efficient for certain problems, not for all the problems. But you can certainly improve this method in a different way. This is the first way to improve this method. Imagine that in finite element method, you have a method called the moving mesh method, where the idea is that the number of meshes is fixed. Suppose you only want to use 1,000 mesh size, and then the moving mesh method means that for each iteration you will move the mesh, not add the mesh, not divide the mesh into two. It's just move the mesh to the singular region, and keep the number of meshes unchanged. This is the moving mesh method in finite element method. But you can do the same thing here. You can do the same thing here by using the so-called resampling schemes. Actually, ideal training set should be contain these three parts. The first part is the so-called pre-selected collocation data size, which means in the beginning you just use some prior distribution, normally uniform distribution to generate points. This is the first type of points. And based on these points, you will adaptively choose some adaptive points. But certainly for some very complex problems, the prior based selection will miss some information. Very likely for very complex problems, the uniform distribution in the beginning lost some information. This will not come back by adaptivity because the uniform sampling in the beginning has lost the information. So sometimes you need a new data sets also based on that prior information to give some possible new information in the beginning, which is lost. So the most ideal training point should contain these three parts. You can use some recycling scales to control the ratio of these three parts and to generate the so-called adaptivity with fixed number of training points. In this way, you can control the number of points. Suppose you use 2,000 points, you can control the ratio of these three parts. You begin with uniform points, eventually you will give you not uniform distributed points, but number does not change. This is the idea, similar idea as in moving match method in finite element. The other way to improve the method is to use a much more complex model. Because in the first part, I just show you the idea. I mentioned that you can use simply Gaussian density to model the optimum density in each iteration, but this is not optimal. Suppose the residual is very complicated. You can't imagine to use the Gaussian density to model this residual distribution. This is impossible. So actually, you can use more complex models to model the residue. One choice is the so-called Gaussian mixture. You can use several Gaussian distribution to model the current density, model current residue. But in this way, you have to compute the coefficients and compute the mean and variance for each components. So the computational complexity will be increased, but still can be negligible compared to the training of a neural network. And you can use much more complex models, such as actually you can use a generative model to model the residue, model the optimum density in each iteration. Generative model means another neural network, right? A special designed neural network which can generate density, generate samples. But you have to care about this. This is actually optimal. You are using a very complex neural network to model the density. This should be optimal, but actually you can imagine that to train for training this neural network, the complexity for training this neural network is comparable to train the PDE solution. Do you know what I mean? If you consider finite element method, you have to solve a linear system, right? After solving this linear system, you will compute the error indicator. If the complexity for computing the error indicator is comparable to the linear system solver, but this is not acceptable, right? So you don't want to do that. So this is the case. If you want to use a very complex model to model the density, optimum density, you want to do this in an optimal way. This complexity for computing this part is comparable to solve the PDE itself. So you have to balance the complexity for each part. But this can be used for some certain very special equations. Suppose that the solution for the equation is density function. Suppose there are a lot of equations like this. The typical one is the Fokker-Planck equation. The solution itself is a density function. For that kind of equation, actually, you can directly model the solution with generative model. Because the solution is the density. You can just model the solution with generative model. And then you will not need to compute another model. This is a very special case. In general, PDE it's not acceptable to use a neural network to learn the density. But for Fokker-Planck type equation, this is a good idea. I will show you by numerical examples. Okay, next I will show you more examples. This is the two-dimensional problems with two peaks. You can see that for this, you have two singularity. If you consider to model the residual, model the solution with a Gaussian density, which cannot be efficient, right? You can imagine that. But in this case, actually, you can use Gaussian mixture as the posterior model. In each iteration, you can use the Gaussian mixture to model the residual. Because the residual should be like this. Residual is similar as the exact solution. So you can't compute accurate solution. So the residual is something like 2 peaks. So this can be modeled by Gaussian mixture. If you consider Gaussian mixture in each iteration, this will be much more efficient than the above RAR. And you can see that the background is the initial training points, and each iteration you add new training points to the 2 peaks. This is another example, but this is the 4 peaks example. In this example, we use a more complex model called subset simulation in statistics community, and we use the risk sampling scheme for this example. It means that we will not change the number of training points. So the point is begin like this, and eventually they will concentrate to the singular part. The number, we will keep the number unchanged. For this example, we just use subset simulation and rescaling. And then you will eventually control the number of training points, and all the points will concentrate to the singularity region. And this is the inverse problem, because for pins you can solve the inverse problem in a similar way. And this is to recover the unknown gamma here. Gamma is a 5-dimensional problem, 5-dimensional function, which is a discontinuous function. This is the typical EIT problem in inverse problem. You can do the same thing here. Here we also use Gaussian mixture, but this is not a finite pink. This is actually an infinite dimension discontinuous. This is a continuous is like a ring. It's not 4 points or 8 points, and something like things like that. Well, for this, we also use the so-called Gaussian mixture. You can see the difference here. If you always use uniform, you can't recover the unknown coefficient. But if you use RAR, you can see that the efficiency is not that good. If you use Gaussian, you can solve the problem, but not that efficient. If you use Gaussian mixture, you can see that the difference is very clear. So the posterior model is very important. This can be problem dependent, depend on how complex of your problem. If the problem is very complex, you should use a more general model. Otherwise, you can consider a simple Gaussian density. This can be very problem dependent. This is the last example. This is Fokker-Planck equation. It's another story. As I mentioned before, this solution itself is a density function. So actually, you can't use a general neural network to approximate the solution. You can't use a normal, fully connected neural network to approximate, because the solution is density function. It means that for density function, you have to require the positivity and the volume conservation for the density function, right? If you consider a simple neural network function, then you can't guarantee these quantities. You have to add a lot of penalty term, which is not good actually. So the idea for this kind of equations, this is the most simple Fokker-Planck equation. This kind of equations actually, the idea is model directed the solution with normalizing flow with a generative model. Normalizing flow is specially designed neural network. It can be used to approximate the density function. I think I can skip this part because normalizing flow, you may confuse about a normalizing flow. The idea is to approximate the density function. The normalizing flow is a special neural network, and they will automatically satisfy these kind of quantities, these kind of constraints, especially designed neural network. This frequently used in density approximation in imaging science, generative model. The most famous one is the so-called normalizing flow. But by using this kind of normalizing flow, you can model the solution with a normalizing flow. So you will not care about the constraint for the density function. And this normalizing flow, actually, the idea is to approximate the density by samples. Normalizing flows means that I want to find a map between this density and the Gaussian density and the simple density, I should say. Suppose Gaussian. You want to approximate this, which is complicated. But now I want to find the inverting mapping from this to Gaussian. If I can find this map, then I can sampling Gaussian through this map to sampling this density. This is the basic idea for normalizing flow for generative model. So idea is very simple. I just model the inverting mapping with a neural network. And then I want to find this mapping. This mapping is modeled by neural network. And then once I found this mapping, and then I can sampling P by sampling with Gaussian. C is Gaussian. C is Gaussian, and this Jacobi for the transformation. So this is the generative model idea. You want to approximate very complicated, uncomplicated density, but now you change the problem into approximating a mapping. You just model the map with neural networks. Once you train the neural networks, you can sampling with Gaussian random variable and then compute the Jacobi to generate new sample for the density. And density have a formula here. It's almost explicit formula here. But the idea is here, but the key issue is how to design this mapping here. The mapping should satisfy two main properties. One is easy inverse, because when you sampling, you have to inverse you have to compute the Jacobi, and you have to do the inverse to get the formula. Otherwise, you have to evaluate the Jacobi of the transformation. So most of the normalizing flow or KRNet or real MVP, this is a kind of normalizing flow. They are generative model. They are special designed neural network to satisfy these two properties. So you can use this kind of model to approximate the solution of Fokker-Planck equation. By doing this, because the Fokker-Planck equation, the solution is a density function. You model the solution with a generative model. You begin with uniform sampling, and then after a few training procedure, you will get the approximate solution. But here, we don't have residue. You have residue, but you care about the solution. The solution itself is a generative model. You mean what I say? You model the solution with generative model, and after a few SGD for training the neural network, you get an approximate solution. The solution itself is a density function. So the solution itself can be an error indicator. You don't need to do another indicator based on the so-called residue, because you are approximating the solution. The solution is density function, and you model the density function with generative model. So after a few iterations for the SGD iteration training the neural network, you get an approximate solution. This solution is a generative model. You can use it to generate new points. You don't need to compute another model, right? So this is the idea why we can use a generative model to solve Fock-Planck equation, because the solution is density, and based on itself, the adaptivity can be done easily. The solution itself is an error indicator. It generated by itself, the points should be okay, right? So because itself can be a good approximation to the solution. So for Fock-Planck equation, the adaptivity is relatively easy. You don't need to compute the residue and compute another model in each iteration. But the difference is here you have to consider the generative model to model the solution. But this is natural actually. The solution is density function. You can't use a general neural network to approximate. So this is the procedure for Fock-Planck equation. It's very easy. You don't need to compute another model. In the beginning, you use a generative model. That's enough. The adaptivity will be automatically done by itself. This is the Fock-Planck equation in the whole domain. So you don't know where the solution is. In the beginning, but anyway, in the beginning, you have to choose the training points. I don't have any choice. I don't know where the solution is. Actually, the solution is around the four points around here. But in the beginning, this is a whole domain computation. I don't know where is the solution. I just generate some training points here. Here, just cover a few regions of the exact solution. I just begin with these training points, and I will train the generative model, train maybe 100 steps by SGD, and then I will obtain the approximate solution, the generative model. The model will generate new points, and then I will get rid of the initial training points. I will generate new points by the solution itself, which is here. And based on this point, I will repeat the training for the neural network. And after a few steps, I will get rid of all these points and generate new samples. And eventually, after 4 steps, the training points like this, and they will capture all the solutions. But this is the procedure for Fock-Planck equation. It's much easier than general equations. But why it's powerful is due to the generative model. It's very convenient to generate new samples. It's a very special case for Fock-Planck equation. You can do very complex Fock-Planck equations with a fractional term, a lot of other models. And also you can do the same thing for deep race. Deep race is the difference because you consider the similar PDE, you will the second order PDE, you will begin with the variational formula here. You can see only one first order derivative. You begin this functional, and then you approximate the solution with neural network function. And this is the so-called loss function. And I just omitted the boundary term here. But here, you want to minimize this. Also, you want to describe this function, this integral here. So the idea is a little bit different with pins. But in pins, you can see that the residual is always positive. You just consider the minimizing the residual, which is always positive. I can go back to the beginning. This is the only difference between pins and the debris. In pins, you are minimizing this quantity. This quantity is always positive. So you based on this current density, current residue, you will learn generate a Gaussian density or approximate optimal density here. But for debris, you are beginning with the variation formula. So there's a little bit different here. Actually, you don't know which one is the best approximation. In the residual case, you can define the so-called optimum density. But for this type of functional, actually, you can define the density like this. A good proposal is like this, or you can define this square. Or that's because that for variation formula, this quantity is not always positive. So you have to consider a positive to learn a density. The density is always positive. So here, when you do the adaptivity, you have to learn the current quantity here. For this quantity, you have to learn the absolute value function, or you can learn the square of this quantity, which is not ultimately is unclear actually. This is like in pins. The pins, there's a unique optimal way in theoretical, the most efficient density. But here, you can give different proposal to do this. This is the difference between pins and the debris. In the other cases, I think I can skip the similar ideas. You can do the adaptivity for debris, similar results. You can do the two pins with debris methods. But in the beginning, you should have a variation formula. Otherwise, you can't use debris. Okay, I think I can almost finish my talk and just give you some very basic idea to do adaptivity in pins and debris. The idea is to adaptively choose the training point in the physical domain. This is coincide with adaptive finite element. You have to refine the physical mesh in finite element computations. But until now, I didn't touch anything for time-dependent problems. Although I just presented an example for Berger's equation, but the equation is very easy to solve. For general nonlinear time-dependent problems, you have to consider some new techniques to describe the time domain. You can't view the time domain and the physical domain together. They are different actually. Physics domain, just a physics domain. The time domain is defined the dynamics. You can't neglect the dynamics of the solution. So yeah, care should be made when you design the method for time-dependent problems. We have some new results for this, and we will combine the finite element in time domain with pins in physics domain, and join these two methods together with adaptivity. This is a little bit complicated actually. It's our new direction for the time domain problems. You can see that there are also other approaches for time-dependent problems. I guess this is given by Minsook. All of them consider so causality for training a neural network for time-dependent problems. The similar idea. They just emphasize that for time-dependent problems, the causality is important. I mean, I usually emphasize that this is dynamics. It's not unlike the physics domain. You have considered in time domain only one dimension. You don't need to care about the high dimensional approximation, but they indeed define the dynamics of the solution. So there should be some care for this time domain. I just leave some reference here. Also, the neural algorithm, they just based on neural network function to develop the dynamics for the neural network parameters. But this is a very good idea, but not a computational framework. But all these works are without adaptivity. We always emphasize the adaptivity in the physics domain. So this is just they just consider some treatment for the time domain. And also, eventually, we want to solve some operator problems. Because if you want to solve a PDE, actually, it doesn't make any sense, actually. If you want to solve a benchmark problem, the very simple PDE, it doesn't make any sense. Because you never compete, you can never compete with finite element or finite difference. They are well-developed classical methods. So the promising idea is to solve some operator learning problem. But in that problem, it's very hard to do adaptivity. So that's not like here, you solve a single PDE, you do some adaptivity in the physical domain. But for operator learning, it's much more complicated because you have to do adaptivity in the physical domain and adaptivity for the parametric domain, another dimension actually, another very high dimension. It's a functional space adaptivity. It's not like in the physics domain. So this is very complicated, but we have some idea for the Bayesian problems, Bayesian inverse problem. When you face these small problems, not small, but special problems, we have some ideas to adaptively solve the operator for the Bayesian inverse problem. But for general operator learning problem, how to do the adaptivity is still in progress. I also list another two reference for operator learning, but this is not for adaptivity, but they indeed give you some idea for learning the parametric operator. And in this paper, actually, there is an adaptive sampling for this parametric model. This is exactly what I want to do for operator learning, but actually the model considered in this paper is a parametric model. I mean that the operator is not that complicated. It's just with a small number of parameters. More precisely, they just consider the Navier-Stokes equations with a few parameters, a real number and boundary conditions, a few number of parameters. They view the real number as a parameter, maybe 2 or 3 dimension, and other parameters. They learn this parameter to solution map. It's a low dimensional operator learning, but still with a very good adaptivity sampling. They can learn a larger range of the real number. And they use some samples to train a surrogate model. And then if we consider a new model with a new real number, they will generate the solution efficiently. That's the idea of this paper. What I want to do is also a very general operator learning for general PDEs actually. This can be the starting point. Yeah, we also have some idea for Bayesian inverse problem. Okay, I think I can stop here. Just give you a few conclusions. For the neural network approximations, we just introduced the so-called deep adaptive sampling. The key issue in the method is the prior and the posterior models. Prior means in the beginning you have to choose the uniform points. Currently, we always use uniform distributed points. And in the middle, in each iteration, you have to develop your posterior models. I have introduced you to use Gaussian density, which is very easy for handle very easy problem. For more complex problem, we can use Gaussian mixture and even generative model for Fock-Planck equation. And as I said, if you want to solve a very simple PDE, the numerical example in this slides doesn't make any sense. I just want to show you that the math process was working, right? But the example doesn't make any sense. It's not meaningful. It's the if you want to use neural network function, actually you have to face very high dimensional problem. Otherwise, you can't imagine to solve a two-dimensional elliptic equation with neural network. It doesn't make any sense. So eventually we will solve very high dimensional problems. The problems should also have a big meaning in some applications. It doesn't make sense that if you increase the dimension of a Poisson equation to the 100 dimension or 1000 dimension, still doesn't make any sense. You have to choose a real application problem, such as the HGB equation in stochastic object control. This can be very high dimensional problem. So I just list a few references here. I also list some recent work by Cai Wei and myself for this HGB equation. Here in this two archive paper, we can solve the HGB equation, nonlinear HGB equation up to the dimension of 10,000 in a single computer. Thank you. Thank you.
Are there any questions or comments?
I have a question about the bounded formula of in the beginning. Bounded formula about solution and neural network. The bounded formula guarantees the convergence of the neural network.
Bounded
Formula in the beginning. Neural
the bounded term, the boundary term, you mean?
No, bounded formula. Next page. Next. This one, this theorem.
Bounded. Okay.
This formula guarantee the convergence of the neural network.
Yes, this guarantees the convergence of the numerical solution to the exact solution, which is bounded by the tolerance. The smaller the tolerance, the more accuracy of your solution. But if this tolerance is very small, you will need a large number of iterations. So you have to balance the tolerance and the iteration. Because for each, if your tolerance is very small, that means that you have to refine the mesh for many times to obtain a very small tolerance. And this is the upper bound. This is the upper bound of a numerical solution. This is not a true convergence analysis. It's the upper bound. The upper bound can be large, actually, depend on your tolerance and also depend on this quantity here, which is unclear. Actually, it's not clear actually. So this is not a rigorous convergence analysis, just the error bound. The meaning that the methods is reasonable, and you have to balance the tolerance and the computational resource. I agree.
Okay.
So here M is respected to residual only, where the bounded terms go.
M is for certain problem you can derive the bound for M, but for general may not be bounded. So this is this is not a clear convergence analysis. This is only a bounded results. But for some benchmark problems, you can certainly derive a bound for this video.
So here you are including only residual. Where is the bounded terms like B terms in the formulation? last function you have the B term, right?
Last what?
In the last function, by formulating, you have residual plus
Yeah,
boundary
boundary
with-
term.
Yeah.
Yeah.
Here, where you have considered.
I just suppose the boundary has been well fitted. Because I just simplified the derivation and simplified. I just want to show you the idea. Actually, for boundary term, you have to do the same thing for adaptivity. So I just assume that boundary have been well fitted. Then just consider only the equation term. You have to do the same thing for the boundary.
There are also convergence rate analysis for your
Convergence rate?
Yeah.
I don't have any convergence analysis, so don't have a convergence rate, but the rate is only for this tolerance. This is very standard derivation. It's not complicated. The rate is just 1 order and a half order for this tolerance. This is only the rate. We don't have any rate depend on the number of points and the number of layers. We don't have such convergence analysis.
Thank you.
Similar as in finite element method, it's very hard to do convergence analysis for adaptive method. You can do a convergence analysis for standard finite element method, but for adaptivity, too many things you can do exact convergence analysis.
Any other?
You have two figures while you are comparing your method and this method, right?
Yes.
Can you explain?
Yes.
Yeah, this one. The highlighted point, how you are just selecting it.
You mean
Yeah.
this kind of points?
Yeah, left
Yeah.
side figure.
This is the authors I just presented. In the beginning, you begin with this kind of initial training points, right? With these points, you will train the neural network to obtain the solution, approximate solution, and obtain the approximate residue, right?
Because the point you are selecting is just a small region, right?
Yes, more reason, yes. Similar as in finite element, you just want to add the mesh into the singularity region. This is the singularity line for the solution. Your solution has this x, this x. Solution has a singularity line here. So the indicator, the residue, the current residue will tells you where the points give you the largest residue. So the new point will concentrate to this continuous line here.
So these are the points handling the singularity.
This point means that within this for these points, the residue for the last step is very large. And for this kind of points, the residue is very small. So you don't need to add new points here in this region. The residue will direct you to put where you want to put the new training points. So the solution, you can see that it's very simple and you just have this continuous and in other regions, very smooth. Similar as this one. In this solution, you have that singularity here, but in the most of the domain, the solution is 0. You don't need to do anything actually.
Can I ask a question?
So
Can-
for the
can-
failure from the neural network,
Can I ask a question?
so each iteration, so you just compute the residue and then find out the failure area. In that case, you are imposing the criteria to determine where is the failure area and where is the success area.
Yes.
So
Yes.
I'm wondering if this tolerance level is the epsilon. I don't remember the one, but this tolerance is changing with the iteration or just fixed.
Okay, that's a good idea actually. In the current algorithm, we just fix tolerance. Yeah, if after a few iterations, the solution is not satisfactory, you can certainly decrease the tolerance and restart the computation. These two parameter, the tolerance is very artificial. There should be a relationship between the residual tolerance and the probability tolerance. This is quite artificial. We have a lot. We should pay more attention on this choice for the parameter, but currently we just fix the number.
These examples, it seems like the assumption is that if you increase the, for example, number of sampling point near the singular area, then the residue is going to decrease and eventually go down,
Yes.
and then it becomes success area, and then you're done. But isn't it possible that the residue doesn't decay, for example?
Yes, very likely. Very likely for very complicated problems. Residue is only a possibility way to do this, but you can also use the solution itself as an indicator and many other things to do. But here, for pins, if the residue is very natural to use, because pins is minimizing the residue. If you can't minimize this residue in a uniform way, you will not do a good job. But for deep rays or other kind of approaches, the residue might not be a good choice. Even if residue is a good choice, how to use this residue is another story actually. As you said, we do have example that you can't find the uniform convergence for the adaptivity. In that case, you have to add some new indicator. The residue is not always work actually.
Also, in this example, you don't show the example for the boundary.
Yeah.
The boundary.
Yeah, if you consider both the boundary term and the equation, you have to balance the two terms. Yeah. It can be much more complicated.
We have a question from an online participant. Let me try to read it. The question is as follows. I believe that extension to extremely high dimensional PDE is always of interest. In this regard, what is the highest dimension you solved under this framework?
At least the two references for the high dimensional case, but not within this framework. Actually, for high dimensional case, actually one is adaptivity. But if the solution is very smooth, adaptivity is not necessary sometimes. But for high dimensional problems, there's another issue actually. I didn't mention today. If you have the experience to compute the solution of high dimensional problems, you will face a very important problem here. When you compute the residue here, let's see this. When you compute the residue for each training points, you have to compute the second order derivative and first order derivative. And normally you will call for some curve for this, and it's automatic differentiation, right? AD, which is well developed. And if you have experience to solve high dimensional problems, this part can be very time consuming. You can't afford the computation for this term. Suppose you want to solve 10,000 dimensional problem, HGB equation, and this part will last for a few months. You can't use it. So the idea for high dimensional problems, one is adaptivity if the solution is not smooth. The other one is how to efficiently compute these quantities. This is another very important issue. I just list the information here. Actually, in that paper, we developed something that got rid of AD. We will no longer use random automatic differentiation. We will use also random difference, random approximation for the second order derivative and first order derivative. All the things are random. If you consider classical approximation or AD, the exact derivation, it doesn't make any sense for a high dimensional problem. So back to your problems, back to your question. Actually, in this paper, we have solved the nonlinear HJB equation up to 10,000th dimension. That's the most of the complex equation I have faced. 10,000th dimensional nonlinear, fully nonlinear HJB equation. If you consider Poisson, it doesn't make sense actually.
Any other questions or comments? Yeah.
So for the 1D Burgers equation, do you have any result without the diffusion term?
No, we don't have that term. If the high term, the solution will becomes regular, right? Add the diffusion term there.
Or delete the diffusion term, only have the convection term. So for the Burgers equation.
You mean advection equation, right?
Yeah, advection
Okay.
equation.
Advection equation, yeah. This we have some example in which paper you can check this paper. We have this example. For this model, actually, the time domain is the most important part. You can see that if you want to use pins to solve the advection equation, it's not easy, even though the equation looks very easy, right? This is the why we consider time domain. This paper here. We have a very detailed computation for the advection equation in this paper. And that's a good point. If you use traditional pins to solve this, looks like a very most simple equation. Doesn't work actually for long-term integral. I mean, for long-term computation, you can solve the problem until 1 second, but not for a long time. So you can check this paper actually. Yeah, yes, advection. You can also check this paper, I guess. Paris also consider advection in this paper. And for this kind of equation, actually, the time domain, the treatment in time domain is very important. Otherwise, you will not get the right solution. It's very interesting, actually.
Any other questions? Okay, so let's thank the speaker again for the great talk.